try to bend this thing the right way. There we go. You all got a report. You want to check it for accuracy and all the other good stuff. The way the midterm was done, there was a variation in the questions, i.e. you get different numbers, but there was also a pool where there were 3 questions. So I can't really send out a solution because there's essentially 22 different versions of the midterm. Now, some of the questions would be similar, but with different numbers. Some of the questions were the same kind of question, but not the same question. So anything that doesn't make sense to you, you just have to do a one-on-one with me and I'll go over them. Okay.
Did you go over, like, did you at all identify our errors?
Oh, I'm sure there were things that I looked at the working. That's what I did. And then I looked at the working, and if WebAssign gave you all the points, I just checked to make sure that there was valid working for it. And if it didn't give you enough, any points or some points, I went and looked at it and figured out if it was a minor error or a major one. So you would get an increase. Now, I don't know how it looks like from your side. I know what it looks like from my side. So can you imagine your score was 210, and then I gave you another 30 points. Your score will now be 240. In my world, it tells me the old score, the points, and a little asterisk. But in your world, you might just see the final score and not realize that I've given you more points. I don't know. Anybody notice that? Yeah. Does it look like you just get a total, or does it tell you the before and after, or anything?
I'm just confused on what the adjustment on there means.
Well, if WebAssign would say you got 0 out of 30 for a question, and I would look at that question and I'd find out that the only thing you did was you got the first half right, but you screwed up on the second half. Well, I'd give you 15 points. If you did almost all of it right, but a +2 turned into a -2, you'd get like 25 points, right? If you screwed up totally, and I agree with WebAssign that what you did was not what you were meant to do, then you get 0 points. So that's the adjustment. I mean, if WebAssign gave you full points, I can't give you more than full points. So I just check. Those questions are easy. I just check, does that work and look like what you would do if you honestly did that question?
Oh. So the percentage that WebAssign has posted, is that with the adjustment already made?
Yes. What I don't know
okay.
is whether it told you the before score. It sounds like they only tell you the after score. Now, if you wanted to know what the before score was, you could go through each question and see what it gave you as a point. And then you could add that up and then look at your new score and compare them.
Okay. Will we be getting feedback on that?
The feedback is going to be that I've sent you a report with all your grades on it. After that, it's, don't know if you missed the early part, but after that, you really just have to look over your midterm and ask me, I got question 4 wrong and I don't know what I did wrong. Do you want to go over it with me?
Oh,
I can do
okay.
that. Okay, so any more questions before we start this topic? We'll get this finished today, that's for sure. And I'd like to get started on the next topic, which is chapter 11, the last chapter. I don't suspect or expect us to finish that, but at least if I do some questions, it gives you a chance to get an early start on next one. So this week's homework is really just going to be this section. And next week's homework will have a lot more sections to it. So anything that you can do early would be great. So chain rule. In Calc 1, chain rule was a very specific process, and it allows you to do differentiation. It allows you to maybe differentiate something like that. And in chain rule, this is called the inside function. And so if you wanted to differentiate it, it would be the function to the power of 10, so that's the power rule, 10 times the function, reduced by 1, that's the power rule. And then you always finish with the derivative of the inside function. and then you would tidy it up, and that would be your answer. So that's what we would call Calc 1 chain rule. Calc 3 chain rule doesn't really look like this. The process, even if it doesn't look like this, is a function of a function process. That's why it's called the chain rule. This is one function raised to the power of 10, the second function. So that is a chain rule. So what do we get in our multivariable world? Well, there are different flavors of this, but here's one. Suppose that x squared plus 2xy cubed was my function, and then the x and the y, these two variables, are themselves functions of another variable. Let's say t. So technically, if I took x and placed 2t cubed plus 1 for the x's, and y 4t squared plus 1, I'm not going to do it, but if we did that, wouldn't z just be a function of t? Right? So x squared would become 2t cubed plus 1 squared. Then it would be add 2 lots of 2t cubed plus 1 times 4t squared minus 1 cubed, right? That's what it would be. But we're not going to do that because we don't need to solve the question. And what you tend to be asked is to find a derivative. In this particular situation, the derivative is always going to be in terms of these guys over here. In this case, only t. So far, so good. So how do you find the derivative of z with respect to t without turning this into some really ugly formula with t's everywhere? Well, we use what's called the chain rule formula. And there's not one of these. There's lots of them. They all are similar. They all depend on the context. So this is the version for this one. The chain rule formula to find dz by dt is this guy here. You multiply the partial derivative of z with respect to x with the derivative of x with respect to t, plus the partial derivative of z with respect to y multiplied by dy by dt. So if you differentiate this guy with respect to x, you get 2x, and here you would get 2y cubed. Times, if you differentiate x, that's this guy, with respect to t, you get 6t squared. Plus, you differentiate this guy with respect to y. Well, partial derivative with respect to y gets you 0. Partial derivative of this gets you 3 times 2, 6 xy squared. Times the derivative of this guy with respect to t, which is 8t. So what we've just done is found a way to get this derivative, and it uses this formula here. A couple of things about this formula. I know these are not fractions. They aren't. But if you look at it, isn't there a kind of cancelling going on here? This piece here, right, these two guys multiplied together is the contribution to the answer that you get from the x's. And this piece here, these two guys multiplied together, is the contribution that you get from the y's to the answer. So you got this guy here and this guy here. WebAssign is very generous, right? What you would do with that, as far as style points go. Just rearranging it a little bit. So you can see you can multiply some numbers together, and you can maybe rearrange the order to make it look a little bit prettier. Typically, WebAssign is happy with this answer, and so am I. Now, if you wanted to be a purist, wouldn't you turn that x into 2t cubed plus 1 and this y cubed into that guy there cubed, and convert this entire answer into t's. But it's pretty impractical and we don't need to. So try that one as your first answer. And if WebAssign says it's happy, I'm happy. If WebAssign doesn't agree with you and you know you've done it right, then you might have to now and again replace the x and y by these two guys and write the entire answer in terms of t. But as far as I know, it doesn't ask you that. Nobody in my other Calc 3 classes said that this didn't work, right? That you had to do something extra to make it happy. So, guy to look out for, the chain rule formula. Okay. Suppose we have a function z equal to x cubed y squared plus the sine of y. And this time, x is in terms of two variables, s and t. And so is y. In this type of question, technically, isn't z eventually a function of s and t? Can you imagine you replace all these x's with s's and t's and all these y's with s and t? Wouldn't this be a function of s and t? So typically what you get asked is to find the partial derivative of z with respect to s. And after that, almost guaranteed, those two guys. So in these questions, it all kind of boiled down to, most of them anyway, this partial derivative, this function, this multivariate function, and you're asked to find these two particular partial derivatives. The first stage is to figure out what this formula here will be in this situation. Let's do the dz by ds guy. So they always end up being two things multiplied together. Now, if you want dz by dx, this guy is going to be dz and this guy is going to be ds. This one here is also going to have the same start and finish. And then you look and you say, z is a function of x and y. So if I do the guy with x and that with x, and this guy with y and this guy with y, essentially, isn't that almost identical to this one? You see, the only difference is it's s's, not t's. But that's because this guy was being asked. Now, if I asked you to find this one, wouldn't it actually be the same formula with a little curly bit maybe, but that's all. So if you're interested, why these d's and why these deltas? These are deltas because this is two variables and it's multivariable. This is a d because x is only a function of a single variable. So if you're a single variable, you essentially get dx by dt. And if you're a multivariable, you get a delta z by delta x. We got a question, Calvin, or are you just stretching? Are we good?
This doesn't seem intuitive.
What, this here would be equivalent to that?
Just the whole, I guess, working with the fact that you now have, essentially you're working with when x and y are equal to some other equation, right?
Yes. Right, x and y are in terms of some other variables. So you're looking at a function of two variables, x and y, but these variables are themselves functions of two other variables. That's the kind of the chain rule, a function of a function. Now, hopefully if I do a few more, you'll begin to see at least how to create this formula and how to apply it. And before I move on, if you look at this multiplication here, a partial derivative of z with respect to x times the partial derivative of x with respect to s. If you think about what the cumulative effect of those two things are, Do you see that the x's are essentially eliminated from the process, and what you've got is a dz by ds? But this is only the contribution that the x's get. This guy, similar looking, but you see the difference here is this is the contribution you get from the y's. So the way I look at it is that you're trying to find this derivative with respect to one of these two variables. And so you get it indirectly. You find this derivative and then the derivative of the other bit. And this derivative times the derivative of the other bit together get you what you're looking for. In this case, dz by ds. Okay, let's see how this finishes then. If you differentiate this function, partial derivative, with respect to x, you get 3x squared y squared plus nothing, so I won't write that down. So that's this bit, times dx by ds, and if you differentiate partial derivative with respect to x, you get another 2s. Now, if you go back and you do the same function, but differentiation with respect to y, you get 2x cubed y from this bit, you get a cosine y from this bit, and then you multiply by the derivative of y with respect to s, which gets you 2t cubed. Are you comfortable about where these 4 bits come from when you see the function that I'm using, the formula that I'm using above? This bit is the derivative of z with respect to x. This bit here is the derivative of x with respect to s. This is the y bit. This is dy by ds. Now, all I'm going to do now is tidy it up. Not that there's really much to tidy up. Well, there is, I just noticed. Those two can multiply and get me 6. And there's really not much I can do with that one.
Can you pull the paper? Yeah, there you go. Thanks.
Right.
Could you technically distribute that 2t to the third?
Yeah, if you wanted to. I'm pretty sure WebAssign would be happy with that.
Okay.
But it would work. Yeah, there's not going to be that much in the way of style points with these questions, mostly because there's so many different variables going around. There's probably very little chance of anything nice happening. You know, like factoring or pulling out a good common factor. I mean, I could have pulled out 2 here, but I don't think that's worth doing, right? There's nothing really going on there. Now I'm going to give you the next level up. This one was 2 variables for z, and each of those 2 variables had 2 pieces. Here's my next guy. W, x cubed plus y squared plus 10 xy z squared. So w is a function of 3 variables, x, y, and z. X is going to be a function of 2 variables, t and s. Y is going to be a function of 2 variables. And z is also going to be a function. Now, you notice that x, y, and z, all 3 of those guys, are functions of 3 new variables, right? Or 2 new variables, I should say, s and t. Now, you might say, but that last one doesn't have an s in it. You're right, it doesn't have an s in it, but that's not a problem, right? Not all pieces have to have all the variables in it. So now we need to create that guy, because the question is going to be find dw by dt, right? We're going to find the partial derivative of this function with respect to one of these 2 variables, and I've chosen t. So to create the formula, w has x, y's, and z's in it. So that means I'm going to have a partial derivative of w with respect to x times dx by dt. And then I'm going to have a second one, dw dy times dy dt. And then I'm going to have a third one.
Those are
dw
partials though, right? Not,
Yeah, every single one of these is partials. Yeah. The only time you're going to have one of those d's is that if this thing here is just a single variable, right? X is a function of d, y, and z as well. That's, I think they only have, maybe have three. I think they've got three questions where it's t in it. Most of the others are two. Are you comfortable about how you create this guy? Because this bit is the key. You get this bit right, it's kind of plug and chug, right? Are you comfortable why there's three pieces in this case, and there was only two here? Does that make sense? Why you would have three different pieces?
so
instead of
essentially
two?
the DWDT, when you say find DWDT,
Mhm.
that triggers us to go, okay, we need to find DW in respect to X and DX in respect to T.
Yeah.
And then vice the other ones. Like, how do you like it's just not.
You're breaking up a little bit, John, but I think you're asking us, are you asking how I know that this is the right formula? Or
Right.
where the pieces are coming from?
No, like you're asking DWDT,
Right.
right? So in saying DWDT, find that. That's when you have to go and. It
That's
looks like
when you
like,
have to. Yes, John.
no, go ahead.
Right. When you're looking at this guy, I have to find dw by dt. You can't get it directly. It's just too difficult. So instead, we can do it this way. Find out what dw by dt is with the x's. Find out what dw dt is with the y's. And find out dw dt with the z's. If you look at each of these multiplications, essentially this guy followed by that guy gives you a piece of the puzzle. It gives you the partial derivative that the x's did, and then what the y's did, and then finally what the z's did. Right? Let me choose another situation. Suppose I had a z, and it was equal to whatever it's equal to, don't matter. And I told you that x was made up of s, t, and p, and that y was made up of s, t, and p. Your question would be to find the partial derivative dz by ds. They would then ask you a different question to find the partial derivative of z with t, and then the partial derivative of z with the third one. Now, each one of these partial derivatives come from here, not, I mean, if they just said to you, find dz by dx, wouldn't you just say 3x squared plus 2y squared? And I don't care what these are because they don't matter. But if you're asked to find dz by one of these guys, that's when this chain rule kicks in. Now, you notice in this case, I've got two variables, right? And there's three guys over here. Two variables. That tells me dz by dx times dx by ds. And then I do the second piece. That is the combination that will find this guy. This bit is what the x is, right? The contribution to the answer from the x's. And this is a contribution to the answer from the y's. Now, if you wanted to do this one, it would looks. Yeah.
Professor, I have a quick question. So just real quick, in the previous example with the find dw dt, why doesn't the dt necessarily show up when doing like the dz over ds? Because it's, oh, I see it. Never mind. I see where I messed up on.
Like,
Yep.
Right, now if I'm doing this one then, dz by dt, different question, right? Find the partial derivative of dz. Do you see the z's with d's and x's? And then won't the next one be that guy? So this combination finds dz by dt. This combination finds dz by ds. If you look carefully, do you see this has got an s in it, but this has a t in it? Do you see that's the only real difference? This contribution gives you the answer from the x's. This contribution, the answer from the y's.
But in the question, z equals x cubed plus 2xy squared.
Yeah.
X is really s plus t plus p cubed, right?
Correct.
And that's where you're taking the partial of it in respect to one of those variables.
Not
Right.
sure what you mean, but that could be correct. It doesn't. It doesn't need to make so much sense to me. It has to just make sense to you.
Right.
Right? So
I
if you're
apologize.
looking at that, no, that's none to apologize for. But when you're looking at this, are you saying, okay, then for me to make sense of what I'm doing, I'm seeing this as you want to find this partial derivative, but instead what you're going to do is get this partial derivative times this one, but together they do the same job as that one. Right? And you need two pieces because, you know, two different variables, two different pieces to the puzzle. Are we good? Right, back to this guy then. If you differentiate this function with respect to x, you will get 3x squared from this piece, 0 from here, and 10y z squared. Then you do dx by dt, and if you differentiate this with t, you get a 2t out of it. Second one, well, I don't know if I've got enough room, but I'll try. This guy, right, with respect to y, you get nothing out of that, 2y out of this, and 10x z squared out of that. And you differentiate with dy by dt, which gets me 3t squared. And then the third one, if you differentiate this with respect to z, nothing, 20xyz times dz by dt, which is just 2t. So the partial derivative of this original function with respect to t is this expression here. Now, all I would do would be to try and tidy it up as best I could. Most of the time, there's not much. Couldn't I just say 2t times that guy, 3t squared times that guy, and maybe this one I could tidy it up and call it 40xyzt, but that's probably the only one of the three that you could do much to. How are we doing? Okay, let's cut to the chase then and look at some homework questions so you get a feel for what they look like. So, I'm going to share. Right, let's try that again because I'm pretty sure I hit the wrong one. Right, are you looking at 14.5 now?
Yep.
Okay, we are ready to go then. I'm getting some kind of weird message off Zoom. If Zoom dies for any weird reason, will you just hang up till I come back in? Because when it puts up weird windows like it's doing right now, it means something's annoying it. Okay. Here is the function z. You can see it's in terms of x's and y's. And this one would be the kind of the first question I did today. Do you know the ones where the x and y are in terms of t? So can you imagine setting up your chain rule and then your answer would go in here? This one is a function of x's and y's, right? Z is a function. And again, it's a single variable. And this is the last one. So there's three that have that single variable thing going, right? So we've got this one here, and x, y, and z are these guys. So let me do that one. I know it's winding backwards, but I think it's worth it. So I'm just going to write this guy down. And can you see that in this case, they only ask you for one answer? And the reason why they can only ask you one answer is if X, Y, and Z are all in terms of just one variable T, then that's it. That's all you can really ask them. Can you see that in the one just below it, Z is a function of two variables, U and V, but U is in terms of two variables, S and T, and so is V. Do you see why they can ask you two versions now? Right. And the
So-
reason there's an S and a T is because of these two guys here.
Professor,
Yes.
just real quick, is
Mhm.
there necessarily a difference between how the DWDT is written in 3 and how the DZDS is written in 4? Like, because one has a normal Ds,
Yes.
but then the other ones have fancy Ds.
Yeah. The normal Ds, that's question 3. The reason that has a normal D in it instead of a partial, which is what the delta symbol looks like, that's delta, but it's a D, right? The reason is that W is a function of three variables, yes. But aren't those three variables also in terms of T? So if I replaced this entire expression with these three guys here, wouldn't W just end up being a function of T?
Yes.
And because it's only a single variable, it gets a D.
Okay.
So DW. On the other hand, if I did question 4 and I substituted these two guys in here, wouldn't Z end up being a funny function with S's and T's in it?
Yeah.
So it'd be a multivariable. If you're a multivariable, you get the deltas. If you're a single variable, you get the D.
Okay. So if it has a normal D, it's just singular variables because of like the DT, for instance. But if it's dealing with multiple variables, it's a special D.
Yeah.
Okay.
Oh, that works. Okay, so I'm getting worried with the windows that are coming here. Don't know what's wrong with my computer. It's getting annoyed with something. Right, so the guy that we're going to return back to is this fella here. And X is going to be 5 sine t. Y is 3 cosine t's. And Z is going to be 2 tan t. And the question asks us to find dw by dt, right? So first thing I would do is set up the chain rule formula that would generate this guy. There are 3 variables here. See them? 1, 2, 3, x, y, z. So I will do a partial derivative with respect to x, dx by dt, partial derivative with y, dy dt, and lastly, partial derivative of z, dz by dt. Now you don't need to be too caught up. That's a delta and that's a d. And is that going to change anything? No, because when you differentiate things, you typically use the same rules. The reason this is partial is because w has 3 variables in it. The reason why this is a d is because x only has 1 variable in it. Most of the time, these guys here will have more than 1 variable, which means everybody's a delta. Now, that guy that we're going to be differentiating, this W fella, there's a little algebra trick that you can use to make your life easier. If I try to do a partial derivative of this function with respect to x and I left it the way it is right now, you'd have a real hard problem because essentially it's a chain rule inside a chain rule inside a chain rule. It would be really ugly. So I'm going to do this. Square roots can also be thought of as half powers. Logs of half powers can be written as a half of a log. Are you comfortable about the rearranging of the original function to make it a little bit easier for differentiation? Right. So that one's a lot easier to differentiate than that. Even although they're the same thing, that looks and is a lot easier to deal with. Now we need to build our function. Well, we've got it here. So I'll just switch pages. So the derivative with respect to t. Right, if you differentiate this function with respect to x, let's see what you get. You get 1/2. A log gets you 1 over the guy. And then you finish with the derivative of this guy with respect to x. So what's that going to get? It's going to get me 2x. That whole thing is just what dw by dt is equal to. You then multiply by dx by dt. And if you differentiate this filler, you get 5 cosine t's. So that's this piece. Plus, if you then do this guy, you'll get 1/2. Here we go. 1/2 times a derivative of a log is 1 over the guy times the derivative of the guy. So that's this piece. And then you differentiate y with respect to t, and that gets you -3 sine t. Plus, if you do the last one with z, differentiate this with respect to z, you get 1/2, 1 over the guy, times the derivative of this with respect to z, times dz by dt. And if you differentiate 2 tan t, you get 2 secant squared t. Right, I mean, that's massively ugly. I had to do it in 3 lines because I couldn't squeeze them into one. But in a lot of ways, it's very similar, right? Especially the first piece of it. Now I'm going to tidy it up a little bit. That 2y cancels with that half and leaves me with a y over x squared plus y squared plus z squared times 5 cosine t's. The second one gets me, actually I should have called that an x. The second one gets me a y over x squared plus y squared plus z squared times -3 sine t. And the last one gets me a z over x squared plus y squared plus z squared times 2 secant squared. And the only thing I can see is that these guys on the bottom are similar to all of them. So I'd pull that guy out as a common factor. And then just have y times that guy. Actually, x times that guy should come first. So 5x cosine t's. Then y times that guy, -3y sine t. And that guy times that guy is plus 2 secant squared t. And that is the answer. So they're big and cumbersome, at least that one was. Think about how to create the chain rule formula. And then once you get to here, just do it as a plug and chug. Just plug each bit in and then, you know, do what you can to make it look good. But you can see you're not going to get a lot of, nothing much nice is going to happen. Okay. This is a version of 5. Z is x to the 4 plus x squared y. X is s plus 2t minus u. Y is st u squared. And z, is it a z? No, there's no z. Okay. That's what we're told. And we're being asked to find. Well, they actually ask you to find 3 different ones, but I'll just pick one at random. One of the 3 things that you're asked to find is ds dz by du. And I should probably put it over here. Now, this guy is in terms of only 2 variables. So start here. Since there are 2 variables, I know it's going to have 2 pieces to it. When I mean 2 pieces, I mean there's a plus and 2 things, right? So we need to set up the chain rule for this situation. There are 2 variables. So what goes here and then what goes here? Well, I know that they all start with a Z. And I know that they all finish with a U. Right? That structure is pretty much guaranteed. So all we need to do is figure out what goes here and what goes here. And whatever goes here, won't the same thing go there? So what's missing in the first one then?
Your
Get
X.
put here. No.
Partial of X. Yeah.
And this one? What goes here? We've got the X's. That's the contribution to the answer from the X's. What else is going to contribute to the answer?
UI.
If you can set that formula up, I would assume that you can find each piece, right? Because you've got everything you need up here. And then you just put them together and make them look as pretty as you can and call it the answer. So that's what I'm going to do. If you differentiate this guy with respect to x, you're going to get 4x cubed plus 2xy times the derivative of this guy with respect to u, which is actually just the number -1. If you then differentiate this guy with respect to y, that guy is nothing, and this guy is x squared. And if you differentiate y with respect to u, you get 2st. Yeah. And then whatever tidying up you think you can get away with, there's really not much. What could I do? I'd stick a negative in the front, I guess. That's about the best tidying up you can do. And when you're finished, as we are here, do you notice that the answer has X's and Y's and S's and T's and U's in it, right? It has a bit of everybody, and that's okay. Any questions?
Does the -1? Yeah, okay, never mind. It distributes between the 4x cubed and the 2xy, right?
Yeah, so another version of the correct answer would be to maybe do this. That would be equally correct, if that looks nicer to you. Any other questions?
So why was the Z portion partial again?
And the reason everybody is partial, including the Z's, Z has 2 variables in it, so it's partial.
Okay.
X and Y have 2 variables in it, so it's partial.
Oh, I see. Okay.
Yeah. If you think about it, you're just differentiating, right, with respect to one variable at any given snapshot. So that little guy is a derivative of Z with respect to X. That little guy is a derivative of X with respect to U. Right? Each one of these pieces, excuse me, is a derivative, right? And it's a combination of them multiplied together and added that allows us to find this guy. How are we doing? Still here? Okay. Okay, let's see where we can go for the next one. There are only 10 questions. We're halfway through them, so we're getting there. Question 6. There's a variable P, and it's a function of U, V, and W. U, and you just got to live with the fact that U, V, and W are themselves functions of X's and Y's. Although that looks weird, it's just as good as any other question. The letters that you use for variables are really irrelevant, right? I could have called this, I don't know, E squared plus F squared plus G squared. And I could have called that instead of X's and Y's. I could have said it was A, E to the B, you know, and so on. So don't get caught up with the fact, how come the X's are here and the U, V's and W are there when normally the X's are here and the other guys are there? It doesn't matter. This guy here is in terms of 3 variables, and each of these 3 are in terms of 2 other variables. And the letters that they happen to use are really not important, as long as you look in that perspective. So in this question, one of the things you're being asked to find would be that guy. This variable in terms of one of these 2 guys, in this case, that one. So we have to figure out what the chain rule formula is, this guy here. Well, the way I look at it is, isn't P in terms of 3 variables, U, V, and W. So the partial derivative with respect to U by dx. The partial derivative of P with respect to V, dV by dx. And the partial derivative of P with respect to W times dW by dx. Are you comfortable about how these formulas are now getting generated? Right. And the reason it's not a single formula, doesn't it depend how many variables are here, especially, right? If this guy's got 3, they're going to be 3 bits. If this guy had only 2, they'd be 2 bits, right? If you want to differentiate this function as you do with respect to U, then V, then W, you probably would have to rewrite it like that, right? If you're going to differentiate a square root, you call it a half power. Now, if you differentiate P, right, with respect to U, partial derivative, multiply by the power, and reduce the power by 1, times something. Isn't this also the inside function? It has a unit, so it's essentially it's its own little calc 1 version. So you have another T 2U, and that is this piece times. Differentiate this fella with respect to X. If you differentiate this fella with respect to X, you get e to the y. Second term, same thing, but now we're using V. And since there's a lot of symmetry in this question, I kind of know that the answer is going to look almost the same, except a 2V, because we're differentiating with respect to V, times this guy with respect to X, gets you that derivative. And then the last one, again, I'm just using symmetry. You would get this guy times 2W. And if you differentiate this guy with respect to X, okay, that one could catch me. What do you get if you differentiate e to the xy with respect to X? Well, you do get e to the xy, but times something, don't you? Times what? The derivative of e to the 5x would get you e to the 5x times 5. The derivative of e to the 20x would get you e to the 20x times 20. The derivative of e to the xy will get you e to the xy times
Why?
thank you. There we go. Now, the next couple of lines just take a whole load of writing, and I'm not going to do it because I think most of this is done. Won't these two cancel out and you'll just get u times this ugly guy, v times this ugly guy, and w times this ugly guy. You could probably pull out a common factor and tidy it up a little bit, which you should, but it's really just time consuming, right? The hard part's done. Making it look pretty, it comes later.
Is there any indication where you can pull the 1/2 times u squared plus v squared plus w squared to the negative 1/2? Pull that out at first so you don't have to write it 3 times?
Oh God, yes, I would definitely do that. And if you did that, you'd get a u times this guy, plus a v times this guy, plus a w times this guy. You can hear it's a little bit prettier. So pull that as a common factor, multiply them times that, you get this guy. Multiply them times that, you get this guy. And multiply these pieces times that to get this guy. So I'm going to take that a little bit further since we got this far, might as well go all the way. One of the rules about style points is that shouldn't it look like the original? Well, do you see that negative 1/2 power here? Should it be downstairs as a positive and at the same time turn it back into a square root? So that would be the final version, the prettiest version of that answer. Are we good? Right, now, just when you think you've got out of the hole, they throw another shovel full of dirt into you. We're being asked to find this partial derivative, but we have to do it when x was 0 and y is 4. Well, here goes. Well, the first thing I notice is that I can get these pieces I'm pointing at with my fingers, right? These pieces here, all the pieces that have x's and y's in it, I can get their values. What I don't know is what numbers u and v are and w. Well, if x is 0 and y is 4, won't u be x e to the y? Won't that be 0 e to the 4, which means u is 0? And won't v, which is equal to y e to the x, won't that be 4 times e to the 0, which is 4? And won't w be, which is e to the xy, be e to the 0 times 4, which is e to the 0, which is 1. So I now know what u, v, w, x, and y are, right? I have numbers for everybody. So watch this space in case I put somebody in the wrong place. U is 0. E to the y becomes e to the 4. Plus v is 4. Y is 4. And e to the x is e to the 0. So that's v, y, e to the 0. W, y in the next guy is 1 for w. Y is 4. And e to the power of xy, well, xy just gets you 0. All over the square root of u squared plus v squared plus w squared. That guy is 0. that guy is 16 and that guy is 4. That guy is 0, that guy is 16, and that guy is 1. So I would get the answer, which is that guy. So if they say to you, not just find dp by dx, but to find it when x is one number, or when, you know, whatever the variables happen to be called, then you have to calculate all the different pieces that are in your formula using these two given guys to figure out the others, and then plug them into your formula and then make it look pretty. And that was question 6 that did that. You notice that's a 2-pager. That's a big question. Ready for the next one? Any questions about that one? Okay. I'm only going to write down question 7 just so I can talk about it and maybe do the intro formula, and that's it. Okay, W is this combination of X, Y's, and Z's. And one of the questions they ask you to do is to find that guy. Will my partial derivative dw by dr, will it have 2 pieces or will it have 3 pieces based on what you can see here? 2 pieces or 3 pieces? Three, agreed. Okay, you want W with respect to R. So differentiate with X and then X with respect to R. That's the contribution that X gives you. Then you do the contribution that Y gives you, and then you do the contribution that Z gets you. And that's as far as I'm going with that one. Right, so you get the answers, you plug in the numbers, and then you find out that they want to know what the answer is when R is 4 and theta equals pi upon 2. So once you've got your answer, right, you start doing all this. Few more of these guys to do, and that's us finished. Question 8 has Z equals the inverse sine of X take away Y, and X is a function of S and T, and Y is going to be a function of also S and T. And one of the things you're being asked to find is the partial derivative of Z with respect to S. The other one is with respect to T. Well, when I look at this function, I see an X and a Y. That means 2 variables. 2 variables mean that the chain rule formula is going to have 2 pieces to it. The first one is the contribution to the answer that you get from X. The second one is the contribution to the answer that you get from Y. This guy here is really ugly looking, so don't expect good stuff because you won't. Does anybody remember the formula for the derivative of the inverse sine function. It's a tongue twister. Anybody remember the derivative of the inverse sine function?
Isn't it 1 over cosecant x?
I like the 1 over part, but not the cosecant part. But 1 over is a good start. It doesn't have cosines or sines or anything like that in it. What it does have is unusual. It has a square root. So what's any other additions before we do it?
Was it 1 plus x squared?
Darn close. 1 minus x
Almost.
squared.
Ah,
Almost got it. That's a pretty good shot at it, right? Now, you want to find the partial derivative of z with respect to x. Well, I know that says x, but this is x minus y, but it's essentially the same thing. It's 1 over the square root of 1, take away whatever the guy is squared, followed by the derivative with respect to x, which is just 1. So that's the first piece. That's just this piece. Then you differentiate this guy with respect to s, you get 2s. Right. If you differentiate this guy with respect to y, you'll get 1 over the square root of 1 take away this guy squared. But you also have to finish with the derivative of this. It's essentially a calc 1 chain rule, right? Derivative, this is the inside function. The first time with x, you got a times 1. But when you do it with respect to y, can you see where that negative 1's coming from? The derivative with respect to y, negative 1. So we took care of the inverse, and then we finish with the derivative of the inside function with respect to y. And then you do this guy with respect to s, and I believe you get negative 7t. So if you want to make it look pretty, you've got a 2s over an ugly square root. 2 negatives make a plus, so you're going to have plus 7t over the same ugly square root. And since they share the same ugly square root, we can put them into one single fraction. So that's as good as that one's going to get. This one didn't have an x is 4 and y is 2, or s is 1 and t is 40. They didn't have anything. That's as far as you need to go. Any questions about that one?
Well, they could have added partial of z in respect to t too, right?
Yeah, and they did. And it would look similar, but not exactly the same. Last question, and that's the end of partial derivatives. In question 10, the variable z is in terms of x and y. And x is really ugly. And y is a little bit less ugly. So z is a function of x and y, and x and y are functions of u, v, and w. So they actually ask you for 3 questions, but we're only going to do one of them. They ask you for this guy, they ask you for the second guy, and they ask you, oh, I forgot the v there, right? U, v, and w. I'm only going to do one, so anybody got a choice? Which one you want to see done? Any preference? Let's do W then, right? It's as good as any. Okay. The key is here. if your answer is going to have 2 bits or 3 bits or 4 bits or whatever it is going to go, it comes from how many variables the original function has. Would you agree this guy has only 2, x and y? So that means 2 pieces. So that's like my skeleton, right? I'm now going to build some flesh onto it. We know this guy is z, and we know this guy is w, and we know this guy is z, and we know this guy is w. So far, so good. Now, don't you just plug in the contribution from x and the contribution from y? We're good. Okay. Let's see where this goes to. If you differentiate this with respect to x, you get 3x squared. And if you differentiate x with respect to w, nothing, 3w squared. Not bad. Plus, if you differentiate the original function with respect to y, that guy gets you nothing, and this guy gets you
Did you miss a
4.
y to the 4th?
Where? In
Because
here?
Yeah,
I
because you
did,
got
yes. Yeah, I did. There you go. I'll squeeze them in. I did miss them. So this guy is 4y cubed. That guy's nothing. This is 4y cubed. That guy isn't just 3x squared, like you said. It's 3x squared plus a y to the 4, which I missed. And differentiating this fella with respect to w, that guy gets you nothing. He still exists. So you're going to get a v e to the w out of that guy. So is there anything I can do to make this pretty? Not really. So 3x squared plus y to the 4. And how about something like that? 3w squared. This one's got more mileage. I can have 4x y cubed v e to the w. Right, it's just a whole load of things multiplied. Now, if the question had just been dz by dw, this would be it, right? You could tweak it a little bit, but this is it. But they gave you this guy. Find the answer when u is 1, v is 1, and w is 0. Right. So I'm just going to rewrite the question over here. This is the derivative we've already found. Actually, I think I'm going to put the w squared on the front. It looks nicer there. Well, if you tell me that u is 1, v is 1, and w is 0, won't that make x u times v plus nothing? So that makes x essentially 1. And won't y be u plus v times e to the 0? And I believe that makes y equal 2. And I already know that u is 1, v is 1, and w is 0 because they told me. So I should be able to put all these pieces together. 3 times w squared is nothing, and nothing times everybody is nothing. So I'm not even going to bother to calculate it because I know it's going to be nothing. Does that make sense? That bit there pretty much destroys it. Now I've got 4 times x times y cubed times v times e to the 0. Well, that's 4 times 8 is 32 times 1 times 1. So I would get the answer, at least for that one, the answer would be 32. So if you wanted to kind of figure out what's this 32 telling us, it's saying if you had a surface that looked like this guy, and it's changing according to some variables called u, v, and w. At the snapshot when u, v, and w are equal to these numbers, and x and y is equal to these numbers, the rate at which z is changing is that it's increasing roughly at 32. So the Z is going higher at that one snapshot in time. Right? It's like a rate of change. How is Z changing with respect to, in this case, the W variable? And we have finished all of the partial derivative stuff. Any questions before we move on to our next section? Are we good? Okay. Now, I know we're not going to get the next section done. I can tell you that right now. But at least it gives you a head start on next week. So if you've got time, I strongly suggest that you do some of these questions, even although your test is going to be a very minor one. And by minor, I mean it's only going to have questions from the chain rule. That's basically all it's going to have in it. So
Yeah,
that's a
but
plus and a minus.
Each question is going to be 2 pages of derivation.
Yep. So it's still going to take you the same time, just less questions, right? So I guess you're not benefiting, but psychologically, people think if I'm only doing one thing, it's a little bit less, right? And it is, because you're only really doing one thing. And hopefully, even if they take forever in a day, hopefully they're not too bad. Any last chance, any last questions, last chance to do it? Eric?
Yeah,
Mm-hmm.
I was thinking, could we go over one more? Just
Sure. Have you got any
yeah, because I
particular?
feel like I haven't really gotten it down. I feel like I need to
Right.
go through it a little bit slower.
Okay, I'm going to show you the homework questions. In case there's one particular one that we haven't covered that you would like to see. If you see one, you can
Yeah,
tell
let's
me.
do. Oh, go up like try number 6.
This one?
Yeah,
I think we did this one, didn't we?
did we?
Yeah.
Oh, yeah, we did.
You know, sometimes because I'm going through quick, watch the video and pause it, and then just take it.
Yeah, I think I'll
Smaller
just do
chunks.
that. I think I need to see this again, honestly. But
There is a lot of, you know, a lot of steps in it, a lot of algebra floating about, and really ugly, but it's very distracting. I mean, it's nice when the answer's 42, isn't it? And it's clean. It's not so nice when the answer is like a thing, you know, 2 lines long. But sometimes that's what you get.
Okay.
Right, we are about to start then our next chapter. In fact, it's our last chapter. It's chapter 11. Let me go into, oh, I got a chat. That might be something. Thomas, your answer is not what you think it is. I know that's WebAssign said it. I'm not going to tell you over the, you know, the waves what you got, but it is not that answer, and it's a good one. So don't worry about it. I'll talk to you at the end if you want to know. Right, let's get this sorted out. Chapter 11 deals with sequences and series. And we are only going to focus on 11.1, which is sequences. This section has nothing in common with any of the others, but that's not a surprise. Would you agree that partial derivatives didn't have much in common with space vectors, right? And space vectors didn't have much in common, probably more, well, it's a little bit more in common, but you know, cross products and the angles between 2 vectors is not really, you know, each little topic in Calc 3 is its own little island. So sequences and series is probably the furthest away island. There is very little overlap that you would notice, and that's fine, it's new. So let's start with what a sequence is. So a definition. A sequence is a list of numbers that have a pattern. Well, one of the things that mathematics likes to do is to look for patterns and relationships, find connections between things, see if there's something structural that we can understand and maybe express in an algebraic way. And sequences is one of those situations. So here's a sequence for you. And the thing about a sequence is they go on forever. Now, if you look at a sequence, a list of numbers that has a pattern to it, which this has, if you understand the pattern, shouldn't you be able to predict the next number? Does anyone have a shot at predicting the next number?
$16.
You want to tell the others correct what you did? Or how, what you
Just
noticed?
seemed like it was adding by 3.
Yeah. That's a pretty straightforward pattern, right? Nothing, you know, we're not talking exotic patterns, you know, that you need a computer in 5 days to figure out. Right. I mean, those kind of patterns are done by, you know, AI programs where they look at things and they try, you know, when they look at the stars, there's AI programs that try and figure out what the heck you're saying because there's just too much noise. These are straightforward patterns. This particular sequence has a name. It's called an arithmetic sequence. When there is a sequence or a family of sequences that have a certain structure to them, they very often get names. Now, what's the structure here is you can start with any number you like. The first number in the sequence is typically called A. Got to call it something, so they called it A. And in this sequence, did you notice that you're adding 3 each time? And when you add 3, this guy is called D, which is short for the common difference. So if I just said to you in English, I have an arithmetic sequence. Its start value A is 10, and its common difference is 6. You could generate that sequence. You agree? If all I tell you is you start with 10 and the common difference is 6, wouldn't you start with 10 and just keep adding 6 till you get bored? Any sequence that has that structure to it is called an arithmetic sequence. And
So
if you know,
why don't you multiply? Why do you just add? Why can't you? I mean, is it
well, can you multiply 1 to get 4 and then multiply the same amount to get 7?
no? But the way you said it was,
Hmm?
the way you said it. That's why I was wondering why it's not always addition. Is what I'm
Oh
trying to say.
no, yeah, but arithmetic sequences are always addition. There are other sequences where you multiply, which is probably what the next one I will do since you mentioned it. Right?
Okay, thank you for clarifying. Sorry.
Not a problem. Not a problem. So arithmetic sequences have the feature that you start with some number and then you keep adding the same amount. This one here is essentially described by A is 10 and the common difference is 6. Right? If I just tell you that and it's an arithmetic sequence, you know how to generate it. Well, let's do a multiplication one. Let's suppose we do this guy. That's a sequence, right? It's a list of numbers. There is a pattern. And we already know that the pattern is multiplication. So what would the next number be?
$48.
would you agree that in this world, to get from one number to the next, you multiply by 2? Why is it 6? By 2, right? Now, in these kinds of sequences, there's a whole family of them. These are called a geometric sequence. Right, so if you start with a number, could be any number, but once you've got that starting number, you then multiply by the same amount, right? Multiply by 2 forever. You call that a geometric sequence, and we have a naming system. The first number is called A, and the number that you multiply by, in this case 2, it's R, is the letter we use, and it's called the common ratio. Those are two of the most common sequences that you will meet in all sorts of situations, right? Compound interest actually is a geometric sequence. Can't think of an arithmetic one right now, but you know, yeah, if somebody gave you $3 a day, wouldn't that generate an arithmetic sequence if you kept all the money? Right. So you could do it with money. You could do it with temperature, right? You know, if you have a place and the temperature is going up by a geometric sequence, shouldn't you be really worried? Because it's going to get big really quickly. Of course, arithmetic sequences can go down the way. If I tell you the common difference is -2, then don't you start take away 2, take away 2, take away 2. If I give you a geometric sequence and I say that the common ratio is 1/10, then let's pick a number. Let's suppose I tell you that you start with 100 and that the common ratio is 1/10, which I'll write as 0.1. Then your geometric sequence will go 100, and then it would become 10, and then it would become 1, and then it would become 0.1, and so on forever. Do you see that that is still a geometric sequence, right? But isn't it one that is reducing in size, not increasing in size? And can't arithmetic sequences increase in size? But they can also have ones that decrease in size. Any questions?
So,
Mhm. Yeah.
real quick, so a geometric sequence is always going to be when we're doing multiples of something,
Yeah.
and then arithmetic is adding.
Yes.
Would that also be true if we were to subtract or divide?
If you subtracted, it would be arithmetic. And if you say divide, you can rewrite divide as a multiplication. So if I went and said, you're going to divide everybody by 2, I could just rephrase that as multiply everybody by 1/2.
Okay.
So dividing is a geometric sequence process, multiplying as well. And adding or subtracting is an arithmetic sequence, is what you're going to get. We good? Okay. Then that's not the only sequences in the world, although those are the two very common ones. This guy is called the harmonic sequence. These guys, there are literally an infinite number of arithmetic sequences, right? Couldn't you start with any number you like and keep adding 5? Or start with any number you like and keep taking away 6, right? You could generate an infinite, uncountable number of both these kinds. The harmonic sequence is this guy. And technically, there's only one harmonic sequence, and that's M. So you can imagine if a particular sequence, and there's only one version of that sequence, then it's probably going to be an important sequence, right? Why would it get a name if it wasn't that useful, right? And it does have a use. We don't need to know it right now. We just need to know what it looks like and that it has a name. Before I do this one, has anybody heard of the Fibonacci sequence? That's a very interesting sequence because the way that you generate a Fibonacci sequence is quite different from all the others. All the others, you kind of start with the number and then do something, right? In this case, you start with 1, then you can imagine what you're doing to it, right? But there's a rule for it. In fact, since I've done this with all the other ones, what would the next one be in the harmonic sequence after 1/5?
Be 1/6.
0.16, right? No biggie there, right? Now, in a Fibonacci sequence, the basic sequence starts with 2 numbers, and the typical Fibonacci sequence starts with the numbers 1 and 1. And then the next number is 2, then the next number is 3, then it's 5, then it's 8, then it's 13, and then it's 21. Now, if you've seen the Fibonacci sequence before, the next question will be obvious. But if you've never seen it before, why don't you just have a few moments to look at what the heck's going on here? It is a sequence, right? It's a list of numbers, and there must be a pattern to it, right? So there can only be a unique answer, right? And it must be sensible in relationship to what you did previously, right?
Can I take a crack at it?
Go for it.
It's the 2 previous numbers added together.
And it is. Now, the Fibonacci sequence, I guess that's the first member, right? That's the granddaddy of Fibonacci. But technically, if you wanted a Fibonacci sequence, couldn't you start with any 2 numbers you like and you would generate it? So, Natalie, give me a number between 1 and 10.
8.
8. And John, give me a number between 1 and 10 that's not 8. Did you say something?
Oh, that might have been me. My mic was still on it.
6.
6, okay. Now, these 2 numbers are the start of the Fibonacci. To get the next one, you add 8 and 6 together, which is 14. To get the next number, you only use the previous 2 numbers. So in this case, 20. To get the next one, you only add the 2 previous numbers. And then to get the next, this is me finishing now, right? Would you agree that that's got a structure that is unique and obvious, right? If it's a Fibonacci sequence, there's only one next number, right? If there's a geometric series, right? There's one number. Harmonic, there's one number, right? Each answer has one unique answer. Same with these guys. And that's important because if you could say, well, a sequence can be any number I want it to be, then you're not really got a sequence, right? Haven't you just got a random list of digits?
So
Right.
just a
And there's
quick,
no pattern. Mhm.
just a quick question. What is the I think I might have missed it. For a harmonic sequence, what makes it
What-
harmonic or what makes it special?
Well, what makes it special is a little bit harder. What makes it the harmonic?
Yeah.
It's 1/2, 1/3, 1/4, 1/5, 1/6. That guy is called the harmonic.
Would a harmonic sequence oh wait, no, that doesn't make any sense. Never mind.
Now, if you tell me it's something to do with music, because when I think of harmonic, I think something to do with music. It might well have something to do. That's why they called it that name. Like a note and a half note and a third note. I don't even know if that's even feasible. But jazz players do some weird notes, so I guess it's possible to have anything, right?
For some reason, I also thought that it would apply to like 1, 2, 3, 4, 5, 6.
Oh, well, it does. It's a reciprocal of 1, 2, 3, 4, 5, 6.
Okay.
Isn't it?
Yeah.
Yeah, if you look at the 6th one, it's a 6th. Right. Now, each one of these guys that we've done, including the harmonic, have formulas. So sequences have formulas. I'll give you an example of a sequence, and I'll probably come back to these guys and show you what their formulas are. But let's just show you how you write down the formula for a sequence. This one is none of these guys, right? This is just, it wasn't important enough to get a name, right? This is just a sequence, and you define it by a formula. The notation is A1, A2, A subscript 3, A subscript 4, and finally A subscript 5. And what you're being asked to do in this question is to find out what the first 5 numbers in this sequence would be. Well, to get A1, don't you just do 1 squared plus 3? To get A2, it's 2 squared plus 3. To get A3, it's 3 squared plus 3. To get A4, it's 16, it's that guy, and A5 is 28. Are you comfortable about how I got the value for each of those particular sequences? So if you wanted to write that sequence down, you would say 4, 7, 12, 19, 28. And wouldn't that represent the first 5 numbers in that sequence? So if you give me a formula, I can create the sequence. Agreed? Yes, no, maybe? We're good? Okay. And there's a group of questions where that's essentially what they do. They give you a formula and they just simply say add the first 5. So wouldn't that be grab a calculator and hit buttons? Right. Now, suppose I gave you this question. Is the number 4093 a member of this sequence? Well, the answer is yes, it is, or no, it's not, right? But we, apart from guessing, don't we kind of need a way to decide yes or no? And so to do it, what you do is you solve, or try to solve, to see if it's possible, that this guy exists. And the formula for this guy is n squared plus 3. Now I'll try and solve it and see what happens. That's a square. So to get n, shouldn't you find the square root of 4090? I'm not quite sure where my calculator. Oh, here it is. Good. So let's just do that. And the square root of 4090, I mean, it does exist, but 63.95. Why is my conclusion? No, this number is not in the sequence.
Has to be a whole number.
It does, doesn't it? You can only be the 40th number in the list, a sequence, right? Or the 41st number in the list. Would you agree it doesn't make sense to say you're the 41.95 number in the list, or the 30.2 number in the list, right? So if you solve that, right, and the answer came out as 42, you would say yes. If the answer comes out as a decimal, or 3.5, or minus 17, oh yeah, why is minus 17 no good? N equals minus 17. Why is that no good? Why can that not be an answer?
Because you have a square.
Well, in this question, it would never happen. But can you imagine a different formula where I could get a negative answer, right? But you're right. Positive numbers, square root's not going to, you're not going to get negatives out of it. I think it's my question that's at fault. Do you know that n has to be 0, 1, 2, 3, 4, right? It has to be a positive whole number. Would you agree if somebody says, where are you in the list? And you said, oh, I'm in position minus 17. That actually doesn't make sense. Isn't the first number 1, the second number sequence 2? There are no go that ways really in a sequence, right? You can't go negative, right? You can't have n equals negative. So if that happened. Now, suppose I went and asked you for the value of the 100th term in the sequence. And we're still using this guy. Well, that's a lot easier to do, isn't it? Just n 100 squared plus 3. So the 100th number in this sequence would be 10,003. Right? We cool? So having a formula is really helpful because it allows you to find numbers in a sequence. It allows you to write down the first 4, 5, 6 terms, whatever you're interested in. And it also allows you to answer questions like, is one particular number in this sequence, yes or no? So having a formula is very useful. And if the question gives you one, you will say thank you. And when they don't, you're probably not going to like them so much. So let's show you how to create a sequence from an arithmetic sequence. How you get a formula, right? Now you remember this guy, the first number is called A and it's 1. And that the common difference was add 3 was 3, right? Remember we did that. When you are an arithmetic sequence, someone found the formula for generating it. It's A plus n take away 1 d. So you want to do the formula for this arithmetic. The nth term in the sequence is 1 plus n minus 1 times 3, and I'd stick it at the front because it looks nicer there. Distribute the 3 and collect like terms. So if this works, shouldn't this formula generate that sequence? Agreed? So what? 1, 2, 3, 4, 5. Let's find this guy. He is the 5th one, so he's called A5. According to this formula, A5 is 3 lots of n, 5, take away 2, 15 take away 2, oh, 13. Did it work? Now, I haven't proved that formula, but will you at least trust me it works? So if you need to find a formula for an arithmetic sequence where A is the first number and D is the common difference, use this guy here and make it look pretty. And once you've got the formula, can't you do all the other things like find the 100th term? Is 403 in the sequence, right? Anything else you might want to know. Now that's how you do an arithmetic one. So if you want the formula for an arithmetic sequence, use that guy there. Right. Let's look for a geometric sequence then. We have 3, 6, 12, 24, and so on. The first number is called A, and the common ratio was 2, right? Times 2 times 2. The formula for a geometric series, or sequence I should say, is A r to the power of n minus 1. Now, A is 3 and R is 2. So there's your formula. Now, it's a little bit clunky. I can't help that. Do you notice that I've put a big obvious bracket around the 2 to the n minus 1? And the reason I did that is if you don't put it there, couldn't it look like 32 to the power of n minus 1? And even if you put a kind of guy there, couldn't you think of it as 3.2 if you're not very careful, especially me? So emphasize it by separation. That means that I can find the 6th number or the 26th number. Let's find this guy, right? He was A4. So if this works, when I plug in 4 here, shouldn't I get 24 as the answer? Well, it's 3 times 2 to the power of 4 take away 1 is 3. 3 times 8, because that's what 2 cubed is. Are we good? Are we good? The next one in our list, I believe, is our harmonic one. So let's look at the formula for a harmonics one. There isn't a special formula like the other two. There just isn't. But to remind you what the guy looks like. And I think it was you, was it Calvin? Actually told us the answer, isn't it? Basically that one. Would you agree? The third term is a third, the fourth term is a quarter, the nth term is 1 over n. So you just got that one by inspection, right? Just by looking at it. The Fibonacci one, now that is a pain in the butt because it's the only one where the formula is not a basic formula like that. The Fibonacci formula, if you want to call it that, actually uses what's called a recursive relationship. And it looks like this. There's variations on a theme, but I'm going to say A1 is 1 and A2 is 1 because in this Fibonacci sequence, you need 2 numbers to start it. So in my case, 1 and 1. And you then do this. The next number in the sequence is found by adding the 2 previous numbers. Now, if I say to you n plus 2, isn't n plus 1 the one just before it, and an is the one just before that? So, if I asked you to find a3, you would take a2, add a1. Let's see how that works. If that's 3, that's 1 less than this, so that's 2, and that's 1 less than that. And we know that these two guys are 1 plus 1. And so A3 would be equal to 2. Right. It's not a formula like this guy, right? It's not plug and chug and you're good. Basically, all I can do is use it to get the next number. Now, once I know what A3 is, can't I now find A4 and A5 and A25? So a recursive relationship is one that looks similar to this one here. So let's spend some time looking at what homework questions would look like. Try and make this a little bit bigger. Okay, I'm ready. Let's see. Right, here is the formula. Find the first 5 numbers. Now, first things first. There is no mention here of to 2 decimal places or anything like that. So you don't just hit the button and write 0.12 or whatever you get, right? You want to keep the answers as exact. So, for instance, I want to find A3, right? It's negative 1 to the power of 2. See what that guy looks like. Oh, can I click on that? No, okay. Negative 1 to the power of 2. So I'm just going to write it the old-fashioned way. Right? Divided by 4 to the power of 3. Agreed? Now, negative 1 squared is 1, and 4 to the power of 3 is 64. So that answer would be 1/64. Everybody's pictures disappeared. Can you lots hear me?
I can hear you.
I can hear you.
Right, I just thought I'd lost you. Not a problem. Okay, Now, in question 2, do you see that they're telling you A1 and they're saying that this is a recursive relationship. The next number in the sequence is 5 times the previous one, take away 3. So let's show you how that works. The first one's a freebie. I already know that's 6 because you told me it was. This number is 5 times the previous number, take away 3. So that's 27. The next number is 5 times the previous one, A2, take away 3. And what's that going to give me? 135, 132. And at this point, I'm stopped doing it because the numbers are too big. But you can imagine 5 times 132, take away 3, 5 times that answer, take away 3, and you've got all your guys. Now, this one is a recursive relationship. You start with 4, so the first one's for free. And then you can go here and you can get the next number. So it's the previous number 4 divided by 1 plus that number, which is 5. Then the next one is messier. It's the previous thing, 4/5. Little bracket around it, the top, 4/5. And then you divide it by 1 plus 4/5, which is what, 9/5. And that ends up, oops, that guy ends up being equal to 4/9. And so on and so forth. I'm going to show you a different way, hopefully, to calculate the value of a sequence. And it's from Desmos, which you would think would be unusual, but actually Desmos can do it for you. First I have to make sure I'm in Desmos. Oh, wrong one. Oh, we're good. I got it. I may have to go back out and then again because of what we've got here. Right, here is Desmos. Let's do a formula, right? What will I call it? I'll call it y equals. Don't know why I'm capitals there. Y equals, and let's say it's n divided by n squared plus 1. Now, Desmos plots things. Let's not worry about what it's plotting, right? But if you wanted to find out the answer to this guy, right? What you do is you copy this fella, put a little bracket, and you put, I believe, let's see if I remember, it's n, comma, the guy. That's good. Let's kill that one off. Add a slider. Click on it. Start at 1. Finish at 5. And go in steps in 1. Now, you see that guy there is my first answer. 1, 0.5. You want the second answer? Oops. I did it. Slide. My slider's not sliding. Ah, there we go. It's just been a pain. There. 0.4. 0.3. Now, do you know that you would turn them into 3/10 and so on? But that's one way that you can do the calculation. I don't know how much time it saves you, but it's another way of doing it. I've lost my window. Here we go. I got it back. Now, the next one looks like this. I'm just going to pick one out at random. Let's get this guy. It's 1 over 2 lots of 4, add 3. And so the answer to this one is an 11. Don't write a decimal, write 11. And if they said that one, which actually they do, it's 1 over 2 lots of 100 plus 3. It's 1 over 203. Are we good? Now the next one is a recursive relationship. And it says this. En is 2 lots of an minus 1 plus 6. And a1 is 4. Right, in English, you would say the next number in the sequence is equal to 2 times the previous number plus 6. So let's find out. A1 is 4. To get A2, 2 times the previous number, add 6. To get A3, 2 times the previous number, add 6. So do you see that the way you get formula is just plug the number in and you got the answer? One of the big advantages of a formula is you can find A100 with one calculation. If you have a recursive relationship, as we have here, if I asked you, and nobody really would, but if I asked you to find A100, wouldn't the only way you'd be able to do that is to find all the other 99 first? Because all the recursive relation does is it tells you how you get the next number. And once you've got that one, you can now get the one that comes after it, right? There isn't a shortcut where you can jump right to the 100th one, right? That makes them much less versatile in calculations. How are we doing?
Doing good.
Good. It's a totally different thing from partial derivatives, right? I don't
And
think you found
vectors.
anything.
And
Better?
vector.
And vectors. Different, better, worse, just different.
Reminds me of
Also-
statistics.
Oh, interesting. Eric, what you
Oh.
saying?
Oh, so how would you find A100 with a single calculation if you would have to know the previous number of that?
You don't. What you have to do is you have to find every single guy, and eventually you'll get to A99. And let's
Oh,
pretend
great.
the answer is 42. You would then go 2 times 42, add 6. Nobody in their right mind would want to find the 100th term in a recursive relationship, right? But isn't that what computer programs are for?
Oh, yeah.
Yeah, and if you do a computer program, that's actually not that hard to program, right? You know, store the last answer and then do a calculation to get the next answer.
Okay.
We are now going to look at sequences, and in particular, all sequences fall into one of these categories. They're always increasing, they're always decreasing, or, it's a funny term, or they're not monotonic. Now, an increasing function, or sorry, an increasing sequence would be one like this. Right? The answers are getting bigger. A decreasing sequence could look like this. They're going downhill, right? They're decreasing. A not monotonic means that it's neither going up or going down, but it's kind of going up and down and then maybe up and down again, right? It's kind of waving around. So a not monotonic sequence might look something like 1, 3, 7, 3, 1. And who knows what the next one would be. Can you see that function increases and then it decreases? If you are one of the top two guys, right, you're always increasing or you're always decreasing. Those two guys, both situations, are called monotonic. It means mono, they're only doing one thing. I'm only increasing, I'm only decreasing. So this word, not monotonic, it kind of makes sense when you realize that these two guys are called monotonic. This is just an increasing version, this is just a decreasing version. Are we good? Now, there's a second thing that we look at in sequences. Some sequences are bounded. And if they're not, then they are called not bounded. Right, let's take this guy here. Would you agree that this function gets bigger and bigger and bigger forever? So this one is not bounded. On the other hand, looking at this sequence, you are bounded if you can be hemmed in between a small and a big number. In this question here, would you agree that this function gets smaller and smaller, but would you agree that it's bounded by 0 and 4? Right? 4 is as big as it's ever going to be, and isn't it going to get closer and closer to 0? So we would say that function is bounded. This one here, because it starts at 1, you might say it starts at 1, that's good, but it's unbounded, right? Because it goes essentially to infinity. Now, a not monotonic function might be bounded, it might not be bounded. Can you imagine a function that went up and down, but it never went anywhere except between 1 and -1, right? An example of that could be this sequence. Now, if you plot that sequence, you'd find out it kind of bounces around, but isn't the maximum range is always going to be between 1 and -1. So this sequence goes up and down, right? It goes up and down, up and down, up and down, but it's still bounded, right? How are we doing? Still okay? So let's look at a sequence and see if we can decide, is it increasing, is it decreasing, and all those good things. So here's start with this fella here. Here is our formula. So it's great when you have a formula. Imagine the value of A1, A2, A3, right? Another way of looking at that is, if I went and said to you, y equals x over 3x squared plus 2, couldn't you sketch it? And if you had a curve that was always going downhill, it would be decreasing. If you had a curve that went uphill, wouldn't it be increasing? And if it went up and down and up and down, it only needs to go up and down once actually to be not monotonic. Which one of those three do you think we're going to be dealing with here? Something that's getting bigger and bigger, something that's getting smaller than smaller, or something that kind of goes up and down a bit? What's your gut feeling for that function? Well, you could always find A1, A2, A3, right? And look at the numbers.
I think it
Let's
will
see.
duck below the x-axis and come up near 0.
Ah, interesting. Well, let's see if I can make that happen. So I've forgotten what that guy is, so I'll go back and find the question and we'll do a little plot of him, right? See what he looks like. Here. So the function was n over 3n squared plus 2. Okay, let's see if I can make Desmos plot some points. Come on, Desmos. There we go. So take care of this guy and call him n over 3n squared plus 2. Okay. Oh, that worked actually. That's cool. Don't want that. And I'm going to do. Got to try and remember the format here. Oh yeah, I remember now. I think it's little n, and I put big N here, and a square bracket, and then I can add a slider, and click on it, and say start at 1, finish at 30, and go up and come back here and go up in steps of 1. Right. So I'm going to shift this guy, and there's the
forgot
first
the-
value.
forgot we don't want to do negative.
Right. Well, unfortunately, well, it kind of does half of what I wanted, but not necessarily the way I did. So I'm going to just play about with this to get the format right. If not, at least I can show you each individual point. But I was hoping to show you. Okay, that's definitely not it. So put that back to N, make that capital N. Now that's good. Now, oh, I remember now. 1, comma, dot, 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 comma. That should make a difference. There we go. Let me change the scale so you can kind of see what's happening. Right, what you're seeing here is actually a plot of the first 8 terms. Now, do you see the first one's what, about 0.2, and then it's decreasing? Let's change that scale even more. There. Would you agree that based on at least the data that you can see, and let's add in some more points. There, that's even better. Would you agree that this is decreasing? Yeah. Would you also agree that it's never going to get less than 0? It's always positive something. So on the bottom side, it's that. And would you agree that the biggest number is that guy there? So isn't it bounded? So this sequence is bounded and decreasing. We go. Now, if you take a little snapshot of that when you want to do Desmos, n comma the formula, n equals square bracket 1 comma 3 dots, I think, comma capital N, and then just change the little slider thing because it'll ask you, do you want a slider, and put, well, if I click on it, you can do it 1 to 50, 1 to 20. Make sure it says step 1 so you're getting the individuals. And that is that guy. So I'm going to go back now, I hope. Okay, cooperate here. There we go. Are you looking at the original function, question 7? WebAssign, can you see question 7 on your screen? Okay, that's the one I just did. So we decided it was decreasing and it was bounded. If you do this one, yeah, it might be decreasing and bounded. It might not be. Do the picture and find out. I like this one, so let me do this one. 4n plus 1 over n. 4n plus 1 over n. 4n plus 1 over n. And for some reason I'm in capitals, so let me get that sorted out. There we go. What do you think? Increasing, decreasing, or doing a bit of both? That should work. Click out, click out. Well, oh, the reason I can't see it is, I believe, a scale issue. Well, there we go. You know, I had to change the scale a bit just to see it. I think that's pretty obvious. Would you agree it's increasing? And if you're increasing, you can't really be bounded if you continue to increase, at least in this case. So I would say it's unbounded as well. it really helps if you can make Desmos do the hard work, right? Because if you see a sequence, it's much easier to tell increasing, decreasing, or whatever. While I'm at that one, let me show you an unbounded one. When you look at sine n, can you imagine sine 1, sine 2, sine 3? There isn't really a pattern here. Would you agree it goes up and down like a yo-yo? It's almost random. So definitely not monotonic, because that's how we describe that situation. But is it bounded? Is there a big and a small value? It never gets better than.
It looks like it has like sequence to it.
Yeah. I'm not sure what you're saying, but it kind of goes up and down, and oh well, it kind of does have a pattern that way. Is that what you're saying?
Yeah, because like between 6 and 8, and at 8 and between 8 and 10, it just looks like inverted. It looks like a triangle that's like inverted.
Yeah. Can you imagine? You've got a normal sine curve, but you're only taking little snapshots at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 radians. That's essentially what you're saying there. And the answer to my first question is it bounded? And the answer is yes. Aren't all the values between 1 and -1? That's all bounded means, right? Unbounded means it zooms off to infinity or zooms down or whatever. It has no specific
And
start or
it being
finish.
between 1 and -1 means it can also touch 1 and -1, right?
Yeah, you're allowed to be equal to them,
Okay.
just not bigger than or beyond them. It's probably a better term. Now we'll move on to a new. Got time? Yeah, we got time. We got a new topic within this. What we've done so far is just kind of introduce you to what a sequence is and how to calculate, if you tell me the formula, how to calculate the 10th term, first 5 terms, whatever it might be. With the aid of Desmos, tell me if it's increasing, decreasing, not monotonic. Tell me if it's bounded or not bounded. Now we're going to look at how to find the limit of a sequence. And this is essentially 50% of this is Calc 1. We're going to do the same kind of things that we would do in Calc 1. So for instance, the first question is number 10, and the sequence is a formula. And you kind of need a formula to do these questions. It doesn't make sense without them. Here's this guy. And we're being asked to find the limit as n tends to infinity. Now, the reason I'm saying 50% of these questions are really essentially Calc 1 stuff is that we did limits in Calc 1. Can you remember the normal technique for finding the limit as n tends to infinity? L'Hopital was a big guy, right? Wasn't there another technique where you divided the top and bottom by n squared or n? Remember that method, right? And for the questions where you use that, and this is one of them, that works perfectly fine. Can you imagine this function here? I can tell you the answer to that limit as n tends to infinity. Do you recognize this particular situation? Okay, here goes. If you want to find the limit of a fraction, one of the methods is called L'Hopital. Remember L'Hopital? We've used him on and off. In this case, you're going to find the limit as n tends to infinity. And if you differentiate this with respect to n, and if you differentiate this with respect to n, and then you notice that these cancel and that these simplify, do you see that the answer you get is 2/3? L'Hopital. What that is telling me is that if you calculated this sequence, right, and you did it, you know, to eternity, wouldn't the answers to the sequence get closer and closer to 2/3? Right, that's all a limit means, right? You're heading towards 2/3.
So does
So-
that lower exponent get discarded when there's a limit to infinity? I don't remember that part.
What's the lower exponent, do you mean?
Um,
Oh,
the n plus 9 n squared.
oh, I apologize, I missed that guy. Actually, the answer's still 2/3, so it doesn't get excluded. So this is what it should have said, but you can tell I'm getting tired.
No problem.
0, 12n. 1 plus 18n. Now, if you plug infinity into here, it still doesn't work because you've got infinity over infinity. So all you do is L'Hopital one more time. And that guy gets you 12. That guy gets you 0 plus 18. And thankfully, you still got the same answer. But that's more by luck than coincidence, than anything else. Let's visualize that. I'm going to go back to Desmos because it's already set up. And I'm going to change this guy to 4 plus 6n squared on the top, right? So a little bracket to make sure it does it. There's 4 plus 6n squared on the top. No. God, you have to be careful with brackets. There you go. Divided by n plus 9n squared. So I'm doing another bracket to make sure that it does it in the order I want it. Right, we comfortable that's the formula? Now, if I click out of this guy and redo the guy, here we go. First, second, third, fourth, fifth, and can you see this guy leveling off very quickly? Now, I said that the answer is 2/3. And let's make this guy, I don't know, red or something. If you hear a dog barking in the background, it's my dog being a pain. I think you hold it. That's it. Let's change it to red. Yeah. Maybe I could shrink this a touch. I want to try and convince you. Would you agree that it doesn't actually take too many numbers before you can see the thing almost on top of it, right? Definitely levels off to 2/3, right? And so you can use Desmos essentially as a check. So let's return back to here and I'll pick another one and we'll do the same process. Let's pick this one. The limit as n tends to infinity. This is Aversion equation 14. And you have n squared e to the negative 3n. Now, this one is also L'Hopital. It just doesn't look like L'Hopital yet. And that's because you need a fraction to use L'Hopital. Are you comfortable that a negative power can come downstairs? You see the algebra? Now, when you have a fraction, you can then differentiate. That gets you 2n, and this guy gets you 3 times e to the 3n. Now, if you plug infinity in, you get 2 infinities is still infinity. Infinity in the bottom means we can't use it yet. I'll do L'Hopital again. So it's now going to be the limit as n tends to infinity. Differentiate the top, differentiate the bottom, and you get that. Now, when you plug infinity in, you have 2 9 times e to the infinity. Well, e to the infinity is infinite, and 9 infinites is infinity. And isn't 2 over infinity 0? So the limit for that one would be 0. And if I put that into Desmos, you would see a whole sequence of dots leveling off at 0. We good? Right. Another one that is L'Hopital but doesn't look like it is this fella here, which is a version of 15, where you have the natural log of n plus 2, take away the natural log of 2. Now what you do here is a log take away a log can be combined into a single log like that. So I've got a fraction, but I got a log. Well, we can do something. You are allowed to switch places. In other words, you can find the log of the limit, and the answer you get will be correct. So if I wanted to find the limit of an ugly square root of somebody, I could pull out the square root and say it's the square root of the limit. So the limit of a log is the log of a limit. The limit of a square root is the square root of a limit, right? You can switch places in the operation. Can you look at that one and just tell me the answer is 1 just by looking at it? Can you tell? Do a
Not,
L'Hopital.
oh,
Right.
not
Well, just do it.
necessarily.
Right. Well, just do a L'Hopital. 1 over 1, right? You get 1, which means that the answer is the limit of 1. Remember, you still do the natural log of it, and that gets you 0. So I didn't ignore the log, I just did it at the end, which is much easier. Last one for today. This is a version of question 17. And we're going to do, again, L'Hopital. By the way, L'Hopital is not the only way that you can solve these questions. I've just picked ones where that's the method that you would use. And when I see you on next Monday, we'll show you other techniques for different situations. This is going to be L'Hopital as well. But this one has to be turned into a fraction. So I'm going to leave that guy. N over 2 multiplied. That guy is the same as this. That makes sense? That guy to the -1, right? Which basically means turn the thing upside down, right? So, L'Hopital can now work. If you differentiate the sign of this, you'll get the cosine of this, followed by the derivative. And the derivative of 2 over x, or as we have 2 over n, you're going to have to trust me, but you get 2 over n squared. Will you trust me? That's what the derivative is eventually. So the derivative of 2 over n is -2 over n squared. Now, you also differentiate the bottom, which also happens to be -2 over n squared. You can now cancel these two out, and you're now looking at a much simpler limit. And then you do what is basically is called brute force. You can replace the n with infinity, and then you do some infinity calculations. 2 divided by infinity is 0. Actually, any number divided by infinity is 0. So cosine is 0, and the cosine of 0 is 1. So this sequence, right, basically this is the n. If you looked at it and calculated it, it would eventually get closer and closer to 1. So I'm going to put that guy into our Desmos and see if we can prove that that's exactly what we got. Let's close a window here and try and find Desmos. Okay, we're having, there we go. I think I've got it. And there we are. So the fella that we were doing is originally n divided by 2. The sine of n divided by 2. And I put a bracket in the wrong place. There we go. Now, our calculation is that its limit should be 1. So let me put y equals 1 in. And just change the scale so we can see it. Now, if you look at the value of this, it looks like it's going all over the place, agreed? But if I do enough terms and I shrink this scale a little bit, it's eventually, I think I'm going to have to change this number to some ridiculous, like 300. Let's try it again. And 300 is going to be a long way away. There we are. Pull it back. Can I check some? And I made a mistake, which is why it's not working. It's that guy. Oh, I did not need 300. Look at it now. Would you agree it levels off at 1 really quickly?
Does it touch 1 though?
It might. There's not a problem if it does.
Okay.
But what is important is that its limit is 1, right? Sometimes it's just a scale thing. That the dots might look like they're on 1, but couldn't they just be 0.999 and you can't tell the difference? Which I suspect is more likely.